Good morning, everyone. Today I am going to discuss with you our next chapter, that is equilibrium. Okay, related to equilibrium. So now I am going to start our equilibrium topic. Firstly, I am going to discuss with you what is an equilibrium. What is an equilibrium? Okay, so how we can define an equilibrium means firstly we need to take a closed system. Okay, a closed system. If there is an open system, then you cannot attain an equilibrium. Now what is equilibrium? Equilibrium means any constancy, means there is some constancy in pressure, temperature, concentration of the reaction. When there is some constancy in pressure, temperature, or concentration, etc., in a reaction, then that is the state of equilibrium. So you can see that if a chemical reaction is carried out in a closed vessel container, a constancy in some observable properties like color, pressure is observed. There is some constancy. Such a state is referred to as equilibrium state. I hope it is clear to you. So this is an equilibrium state. Okay, now what are the characteristics of equilibrium? Before that, I want to explain you a graph related to the equilibrium. For example, suppose I want to have concentration versus time graph. Okay, concentration versus time graph. Okay, so the concentration, suppose this is my reactant, and this is my product. A is my reactant and B is my product. So with time the concentration of A decrease, and with time the concentration of B increase. It can be same or it can be different. Concentration can be different, but after a particular time there is constancy. Means, see here, if I say that this is my particular time, after this one the concentration of A and B remains constant. I am not saying that it is equal. It may be equal or it may not be equal. Okay, I hope I am clear to you that if there is any constancy in concentration, then state of equilibrium is reached. So this is my state of equilibrium. Okay, state of equilibrium. Now what are the characteristics of equilibrium? How we can say that the system is in equilibrium? The rate of forward reaction is equal to rate of backward reaction during equilibrium condition. We have, suppose, A to B. We want to go from A to B. So for that, this is just a kind of reversible process. Means it's a reversible process. Equilibrium is reached in the reversible process, that A can be converted into B, and by the changing in some conditions B can be converted into A. I will explain it to you in Lee-Chatelier principle. So first characteristics is rate of forward reaction is equal to rate of backward reaction. So how I can make a graph for the rate versus time? See, this is A, this is B. So rate of forward reaction is going to decrease and the rate of backward reaction is going to increase. But here I am making this constant. Means I am putting. Means at this time, this is the state of equilibrium. This is state of equilibrium. So here this is rate of forward direction. This is rate in the backward direction. Means B is converting into A. And at equilibrium, our rate becomes constant. Okay, our rate becomes constant. Next characteristic of equilibrium is what? Next characteristic is it occurs only in closed vessel. Only in closed vessel means in open vessel we cannot say, because in open vessel you can understand that if there is formation of any gas in the open vessel, it remain escape, it will escape from the system, so we cannot get back our reactant, because if two products are going to combine to form a reactant, then how if CO2 for example is removed, then how they will react and convert it into the reactant itself. So equilibrium is always attained in the closed vessel, not in the open vessel. In open vessel, gas particles or something is there uh, that will escape, and we will not get the reverse process again. Okay, so it is only possible at the given temperature both the reaction occur at the same rate, means I told you that the rate of forward reaction is equal to the rate of backward reaction. Okay, so all the measurable property remains constant, like I told you that during equilibrium pressure remains constant, temperature remains constant, concentration remains constant. When equilibrium is attained, one of its parameter remain constant at a given temperature. The same point magnitude of such quantities at uh, any stage indicates the extent to which the process has proceeded before reaching equilibrium, means I will help you in calculating the equilibrium concentration, and from that you will get the magnitude of the quantities, which will help you to know to up to which concentration our equilibrium has been attained, our reaction has taken place. Okay, so we covered characteristics of equilibrium. Another one is we covered the closed vessel, constancy should be there, and one another that a catalyst cannot can help in attaining equilibrium fastly, attaining equilibrium fastly, but it will not change in the product. It will not change the product or reactant or reactant, means catalyst only help to attain the equilibrium fastly but will not change the product. Okay, so the next one is our dynamic equilibrium. Now what is dynamic equilibrium? Suppose I have this closed vessel. Okay, I have this closed vessel, and I have this ice cube and water over it. Okay, I observe the mass by taking a weighing balance, and in the weighing balance, suppose the mass of the ice cube and the water is mass of the ice cube and water is suppose 2 gram. Okay, so after time passes, the ice cube is going to melt, and the whole mass remains constant after some time. Suppose it is 1.5. Suppose it is 1.5 gram after converting. Okay, so it remains at 1.5 after a lot of time. But why it remains this much amount? Because once this is gone to the one of the particle of ice cube is gone into the water molecule, the water molecule is going to strike this ice cube, and this is the state of equilibrium when one is converting into another and the another one is converting into the one, means ice is converting into water, in the meanwhile water is converting into ice simultaneously. This is the simultaneous process. So we think that there is stop of reaction, means there is no change of equilibrium, there is no change of phase, but still it is dynamic in nature. means dynamic means always processing, always there is change, there is some change. We cannot see it with the naked eye, but there is a change. So this is dynamic equilibrium. See, chemical reaction reaches state of dynamic equilibrium in which the rate of forward and the backward reaction are equal and there is no net change in the composition. I will explain to you the dynamic equilibrium, that it is required, it is the equilibrium state. Equilibrium state is always dynamic in nature. Okay, now I have explained to you the equilibrium state too. Next one is equilibrium is not a static equilibrium. Static means stops it stops somewhere and it is not moving here from here and there. Okay, so it is dynamic in nature. Next one is equilibrium law or law of chemical equilibrium. So how I can define equilibrium law or law of chemical equilibrium? Suppose I am writing a balanced chemical equation AA plus BB in equilibrium with CC plus DD. Okay, if I want to write law of chemical equilibrium, then the law of chemical equilibrium, we can write an equilibrium constant for that. Equilibrium constant for that. Now, how I can write the equilibrium constant? This is the product of concentration of products, raised to power their stoichiometric product, raised to power their stoichiometric coefficient. These are stoichiometric coefficient. These are my products. C and D are my products, and small c and small d are my stoichiometric coefficient. Divided by product of reactant raised to power their stoichiometric coefficient. Now, equilibrium constant, the law of chemical equilibrium tells us that in a balanced chemical equation, the equilibrium constant will be written as the product of concentration raised to power their stoichiometric coefficient to the product of concentration of reactant raised to power their stoichiometric coefficient. Okay, at a given temperature. This is, always remember, all the reactions are at a given temperature. The product of concentration of the reaction products raised to the respective stoichiometry coefficient in the balanced chemical equation divided by the product of the concentration of the reaction raised to their individual stoichiometric coefficient has a constant value. Always remember, if I write this equilibrium at 450 Kelvin, okay, this equilibrium constant at 450 Kelvin. So at 450 Kelvin, this equilibrium constant value will not change, even if we are changing the concentration, because if we are changing the concentration, product concentration, then the reactant concentration is automatically going to change, and with that again we will get the same equilibrium constant at 450 Kelvin. Means the temperature is very much important. Temperature is very much important here. Means if temperature changes, then equilibrium constant value also get changes. Okay, I hope I am clear to you. Means K depends upon the temperature, but it doesn't depend upon pressure, concentration, etc. Okay, so this is our equilibrium constant. This is Kc. Why it is Kc? Because this is, we are using for concentration terms. If I want to write, suppose I want to write Kp for this. Okay, Kp is equilibrium constant, equilibrium constant at constant pressures, at different pressures. Okay, equal to nRT. This is ideal gas equation. Ideal gas equation. And P is equal to N by V RT. So what is number of moles by volume? It's concentration. Concentration is molarity. P is equal to CRT. If I want to write Kp, Kp will be for a balanced chemical equation. Suppose this is A gaseous, BB in equilibrium with C plus DD. If we want to write the Kp value, so for that, pressure of C power C, I need to write pressure of C power C. Again the same thing. The product of pressure of products raised to power their stoichiometric coefficient to the product of pressure of partial pressure of concentration, partial pressure of reactants raised to power their stoichiometric coefficient. So these are the product of products raised to power stoichiometric coefficient divided by product of reactants pressure raised to power their stoichiometric coefficient. Okay, so I form this formula. So I am going to put this formula in this Kp value in terms of concentration. If I want to calculate Kp in terms of concentration or Kp in terms of Kc, then how I am going to write it? Concentration, R is constant, P is the same one, C D RT D CART A CBRT B. Okay. Now, if I can write this constant separately, C power C, CD power D, CA power A, CB power B. Okay. So RT power C, RT power D, RT power A, RT power B. Okay. So this is, if the base of the base is same, then power is going to add. So C power C, D power CD power D, CA power A, CB power B, RT power C plus D. Again the same in the numerator, in the denominator, RT power A plus B. If the base is same in the denominator and numerator, then can I write this as K power C? As I have already told you that the concentration product raised to power stoichiometric coefficient, uh, the ratio of concentration of product raised to power their stoichiometric coefficient to the ratio of product of reactants raised to power their stoichiometric coefficient is Kc, then RT power C plus D minus A plus B. If base is same in the numerator and denominator, then power is going to get subtract. Okay, so Kp is equal to Kc dot RT plus RT power C plus D minus A plus B. What is C plus D minus A plus B? This is delta Ng. Means you are going to take only the gaseous powers here, gaseous stoichiometric power here. Okay. Now, what is equilibrium constant? Equilibrium constant is nothing but the Kc that we have already explained. And now, what is its application? Okay. So, equilibrium constant, equilibrium for the backward reaction is the inverse of the equilibrium for the forward direction. Application of some equilibrium constant, initial value of Kc doesn't depend upon the initial concentration, because I told you for a given temperature, we have already covered this, for a given temperature the equilibrium constant value will not change even if we are going to change its concentration. And the next one is equilibrium constant is dependent on temperature. And if I want to write, suppose for A to B, A to B is a forward reaction, and B to A is a backward reaction. If I want to know the equilibrium constant for this backward reaction, how I can calculate? Kc is the forward direction, forward reaction. Kc is my what? Kc is my equilibrium constant. For the backward reaction, Kc dash. Suppose it is Kc dash, then I need to write Kc dash is equal to 1 by Kc. Okay, 1 by Kc. So how I can explain it to you? Suppose I have a balanced chemical reaction AABB in equilibrium with CC plus DD. I can write Kc as C power C, D power D, A power A, B power B. Okay. This is for the forward direction. For the backward direction, suppose it's Kc dash, but now for the backward direction, these are the reactants and these will be the products. Okay. So A power A, B power B, C power C and D power D, because these are the reactants now, these are products. Okay. So can you see, if you are going to compare 1 and 2, then can you say that Kc is equal to 1 by Kc dash? It's the same, because this is just to, if I rewrite it by taking a reciprocal, 1 by Kc inverse is equal to C power C, D power D, A power A and B power B, right? Am I clear to you? So Kc will be equal to Kc 1 by Kc dash. Okay. Now the next one is types of equilibria. There are 4 types of equilibria that I have mentioned here. Now, equilibria is the state of constancy, means there is a constancy in temperature, pressure, volume and something. Okay. Now, what is physical equilibria? Physical equilibria when there is a change in the phase. Okay. If there is solid to liquid change, like I have explained to you ice and water with ice water example. Okay, ice is going to convert into water and water is going to convert into ice. Okay, liquid to gas, liquid to gas, and liquid to gas like water in the liquid state and water in the steam state. Okay, gaseous state. And the solid to gas, that is sublimation. So iodine solid to iodine vapor. This is just the change, the color intensity. Suppose a solid to gas, because iodine sublimes to vapors. Okay. So during the sublimation, this is a physical equilibrium. This is a physical equilibrium, just change in the state. And here the constancy of the mass. Okay. Here the constancy of the mass. After some time, here the constancy of pressure because of the gaseous state. After some time, after attaining the equilibrium, now here the constancy of violet color. Actually, iodine vapors are violet in color. Iodine solid is violet in color. But with increase in concentration of color in the vapor state, we got to know that after attaining the equilibrium, violet color remains constant. Means the intensity of color do not change after some time. Okay. So this is my physical equilibrium. This is my physical equilibrium. Okay. Now the next one is, this I have completed, like evaporation. Okay. Now the chemical reaction. Suppose I have this chemical equilibrium. Okay. I have this CaCO3 solid. After heating, CaO solid plus CO2 gas. Okay. So after measuring the pressure, after some time, after attaining equilibrium, we got a kind of equilibrium in a closed vessel. Remember, equilibrium always attained in a closed vessel. Okay. So after some time, with the constancy of the pressure of CO2, we got to know that the equilibrium has been reached, and this is a chemical equilibrium because chemical reaction is taking place. Now after that, What is homogeneous equilibrium and what is heterogeneous equilibrium? Homogeneous means same throughout. Okay. Homogeneous equilibrium means if all the reactant and product are in the same phase, means in the gaseous phase, in the liquid phase. For example, N2 gas plus H2 gas in equilibrium with 2NH3 gas. In equilibrium with 2NH3 gas. So this is a kind of equilibrium that we have attained. Okay, this is homogeneous because nitrogen is in gaseous state, hydrogen is in gaseous state, and the product is also in the gaseous state. Now, what is heterogeneous equilibrium? What is heterogeneous equilibrium? When all the reactant and product are not in the same phase. Like in this example, CaCO3 solid is in equilibrium with CO solid plus CO2 gas. Okay. So now the calcium carbonate means it is not in the same state like CO2. These are in the different state. So this is heterogeneous equilibrium. Okay. So see, homogeneous equilibria, reactant and product are in the same phase. Heterogeneous equilibria, reactant and product are present in two or more phases. Okay. For the chemical equilibria, this see, equilibrium can be achieved from either side. Equilibrium can be achieved. You can start from the reactant side, you can start from the product side. Equilibrium can be achieved from either side. It is dynamic in nature. It is dynamic in nature. It is not static in nature. There is no change in concentration of various species. After attaining an equilibrium, there is no change. There is a constancy. Observable properties become constant and equilibrium is attained rapidly by the presence of catalyst. I have already told you that catalyst is not taking part in the chemical reaction, but it helps in attaining the equilibrium fastly. I hope I am clear to you. Okay. Now, what are the factors affecting equilibria? But before that, I need to talk about the Lee-Chatelier principle. If what is Lee-Chatelier principle? If when a reaction is in equilibrium and we are changing any of the observable quantities, then equilibrium will shift towards that direction which counteract that effect. Means we do not want the equilibrium do not want to change the state. It is going to move forward or backward according to counteract the effect. Okay, so this is Lee-Chatelier principle. You can read it here. Lee-Chatelier principle, a change in any one of the factors that determine the equilibrium condition like temperature, pressure of a system will cause the system to change in such a manner, then it will change in such a manner so as to counteract the effect of a change. Okay. Now, what are the factors affecting? These are the four factors that affect the equilibria. Effect of change in concentration, effect of change in pressure, effect of temperature, and effect of inert gas. Now let us see what are the effects, how they are going to affect equilibrium. Okay. So first effect is effect of concentration. Effect of concentration. Suppose reactant and products are in equilibrium. Suppose I am adding products more. Product is more. So the equilibrium will shift towards the backward direction. Equilibrium shift towards backward. Because if product is going to react with each other, then the reactant is going to form. In short, there is no change in equilibrium constant. Equilibrium move towards backward direction. Now, if we increase reactant concentration, so the reactant is going to react with each other and is going to make the product to counteract the effect. Means system undergoes a change. System is going to get changed to have no effect. Equilibrium move towards forward direction. Towards forward direction. Okay, next one. Now the next one is effect of pressure. Effect of pressure. As we know, pressure is equal to N by V RT according to ideal gas equation. Ideal gas equation. Suppose I have AA plus BB in equilibrium with CC plus DD. Okay. After that, if I can say this is my gaseous, for example, N2 plus 3H2 gas. This one is also gaseous state, 2NH3, which is also in the gaseous state. So if I say that the number of moles in the reactant side is more than the number of moles in the product side. Okay, so if I'm adding hydrogen gas, or the number of moles I am adding, number of moles of the gases I am adding, then the equilibrium will shift towards the product side. Okay, number of moles of gases adding, then equilibrium shift towards forward to counteract the effect of increasing the moles. If number of gas molecules decreasing, then equilibrium will shift towards backward direction. Okay, equilibrium will shift towards backward direction. So this is regarding effect of pressure. After that, the temperature effect is also very important. Temperature effect. Suppose we are talking about exothermic reaction. Exothermic reaction. For exothermic reaction, heat is going to get released and delta H will be negative. So I can say A plus B in equilibrium with C plus D plus heat. Okay. So if I am increasing temperature, there are two cases: increasing temperature where I put the heat I have put in the forward direction. So on increasing the temperature, it is going to go in the backward direction to counteract the effect. What will be the direction? Backward direction. Okay. Now, if there is decrease in temperature is where? Here we have put no heat, so it is going to move in the forward direction, because heat means the temperature is increasing here. Temperature is decreasing here. Here we are decreasing the temperature, then equilibrium will shift in the forward direction. Forward direction. Okay. Okay. So next one is endothermic reaction. Next one is endothermic reaction. For that, delta H will be positive. Okay. A plus B. Endothermic reaction means reactant is going to absorb the heat and product is going to get formed. Okay. So now, if there is increasing temperature, means increase in temperature, here we have temperature, so it is going to move forward in the forward direction. If temperature decrease in temperature, it is going to move in the backward direction. Okay, could you understand? I hope I am clear to you. So this is temperature effect, and the next one is, I am going to read it from here. Effect of inert gas addition. If the volume is constant, the addition doesn't change partial pressure or the molar concentration. Means inert gas is not going to affect. Inert gas means it is not going to react with anything. So see, the effect of concentration change. If the concentration of reactant is increased, equilibrium will shift in the forward direction and vice versa. Effect of pressure change. No effect if the number of moles of the reactant and product are same. If there is change in the number of moles, equilibrium will shift, having smaller number of moles when the pressure is increased and vice versa. Means if the pressure increase, number of moles is also going to increase. So the equilibrium will shift in that direction where the number of moles is going to decrease. See, here the number of moles are increasing. Number of moles, if the pressure increases, number of moles here increases. So equilibrium will shift in the forward direction to get a lower number of moles and get a lower pressure. Okay. Now the temperature effect for exothermic low reaction temperature favors formation of reactant. Means if the temperature uh, decreases, if the temperature decreases, then it is going to move forward. If temperature increases, it is going to move backward. Okay. So I have covered all this. Now this is the application related to the equilibrium constant, and it is most important from exam point of view. It tells us about the extent of reaction, that how much reaction has already completed. So if I put the Kc for the three Kc values, if the Kc values is less than 10 to power minus 3, is less than 10 to power minus 3, if it is in between 10 raised to power minus 3 to 10 raised to power plus 3, if it is above 10 raised to power 3. Okay. This is 10 raised to power minus 3. As you know, in the numerator, we will have the product concentration. So the product concentration should be too low to get this much value, minus 10 power minus 3. So here the equilibrium is almost, we cannot say the equilibrium, we can say the reaction hardly proceeds. Means there is not any reaction, hardly proceeds. Okay. If 10 raised to power minus 3 to 10 raised to power minus 10 raised to power plus 3, then this is the equilibrium state, complete equilibrium state. Okay. If it is greater than 10 raised to power 3, then reaction is more towards product, more towards product. Here, more towards reactant. Okay. So you can see reaction proceeds rarely 10 raised to power minus 3. If it is greater than 10 raised to power 3, the reaction proceeds nearly to completion. If Kc is in between 10 raised to power minus 3 to 10 raised to power 3, then the reaction is in equilibrium. Okay. Now, the next one is predicting the direction of reaction. Okay. So, how I can predict? So, for that, I need to choose another constant, another quotient, reaction quotient. Okay. Reaction quotient, that is Q. For Q, the formula is same as that of K, but the concentration is not the equilibrium concentration. Concentration here we are putting is not the equilibrium concentration. So we are writing it as QC. See, if QC is less than Kc, if QC is equal to Kc, and if QC is greater than Kc, now where the reaction is going to proceed, where the equilibrium is going to move. Okay. Now if Kc is greater than Qc, means Qc wants to wants to move towards the equilibrium, because if a reaction can form a equilibrium concentration, then it needs to move towards the equilibrium. Okay. So how QC can relate to Kc? If the concentration of product is going to get increased, because if this is going to get increased, the QC value is also going to get increased. So reaction move towards forward, because in the forward direction only we are getting products. Reaction move towards forward direction. Forward direction. If QC is equal to Kc, then this is the equilibrium state. If Qc is greater than Kc, means it needs to come down to Kc, then reaction move towards backward direction. Towards backward direction. Okay. So I hope I'm clear to you. See, QC less than KC, then the reaction net reaction goes from left to right, means the reactant to product. QC greater than KC, then the net reaction goes from right to left, means the product to reactant, and the QC is equal to KC, then there is no net reaction occurs, means there is equilibrium condition. Okay. Next one is, what is the relationship between K and G? Okay, K and G. Delta G, I can say, gives free energy. Delta G, K is the equilibrium constant. If delta G is negative, then the reaction is spontaneous, means feasible, means this reaction occurs by itself. If the delta G is positive, means non-spontaneous, means non-feasible, this doesn't occur by itself. Okay. But for the equilibrium condition, delta G should be 0. For the equilibrium condition, delta G should be 0. So that's why delta G naught is equal to minus RT ln K, means it's an equilibrium condition. Okay. It's an equilibrium condition. So how I can write K here? I can write delta G naught minus RT ln K. If ln, this is the natural log and the anti of it, e power minus delta G naught by RT is equal to K. K can be written in terms of delta G naught as like this. Okay. So this is my delta G is negative, reaction is spontaneous, means it proceed in the forward direction. Delta G is positive, reaction is non-spontaneous, it proceed in the backward direction. Delta G is 0, reaction has achieved equilibrium. Reaction has achieved equilibrium. Okay, I hope I'm clear to you. Now the next one is all concepts of acid and bases. All concepts mean that you have read in the 10th class. Okay, you have read in the 10th class. These are some of the old concepts. Okay. See, acids are something that is sour in taste, and base are something that is bitter in taste and soapy touch. Soapy touch. And acid can char our skin. So this is the old concept. Acid turns blue litmus to red, liberate hydrogen on reacting with some metals. Bases turn red litmus to blue, taste bitter and feel soapy. Salts are formed when acids and bases are mixed in the right proportion. So this is the neutralization reaction, means when acid and base react with each other in a simple proportion, you will get salt plus water. Okay, you will get salt plus water. This is neutralization reaction. Okay, now this I am going to explain you in the acid base concept, modern acid base concept. So there are three modern acid base concepts. From there we get the exact definitions. Okay, so we have three modern acid base concept, that is Arrhenius acid base concept, Lewis acid base concept, Bronsted acid base concept. Okay, see, according to Arrhenius, what is an acid? Acid is something Acid is a chemical that can donate H plus in aqueous solution. H plus in aqueous solution. For example, HCl, it has H, it can donate H plus in the aqueous solution. H2SO4, it can donate H plus in the aqueous solution. Now, base. Base is something that OH negative in aqueous solution, that can donate OH negative in aqueous solution. Remember, acid and base is in aqueous solution. Okay. For example, KOH, it can dissociate and into K plus and OH negative. It can donate OH negative in the aqueous solution. NH4OH, it can dissociate and it can give OH negative in the aqueous solution. So this is arrhenius acid base concept. Now after that I am going to explain you Bronsted acid base concept. See, if I break this, H plus Cl minus KOH, K plus OH minus. So this is acid base concept by the Arrhenius. Now what is Bronsted acid base concept? Bronsted acid base concept is acid is something that can donate H plus ion to the other substance. Remember, the aqueous solution is the limitation of Arrhenius acid base, because he said that in only the aqueous solution and the H plus is going to get removed. He didn't take any other solution, any other solvent. But here the Bronsted took H plus ion to other substance, any other substance. Okay, that can accept H plus. For example, that can donate. Other substance can accept, but the acid can donate H plus ion. For example, HCl, NH3. NH3 has lone pair. Lone pair can accept, means negative can accept the positive. That's why this is an acid. This is a base. Okay. Cl negative, NH4 positive. Here it's a base. Base is, according to Bronsted, base is something that can accept H plus ions. H plus ion from other substance. Here donate H plus ions. Here accept H plus ions from the other substance, like this. Base is something that can accept H plus ions. Now, what is Lewis acid base concept? Lewis acid, Lewis base. Lewis acid that can accept electron from the other substance. So our substance should have a vacant d orbital, to accept the electron. Like AlCl3. It doesn't have the complete octet. 6 electron is there around aluminium, but it should have at least 8 electron to complete the octet. So it needs to take the 2 electron from the other substance. That's why it's a acid. Another famous example is BF3. BF3, it also has, boron has 6 electron around it, so it can accept the electrons. Okay. Now base is something, Lewis base is something that can donate electrons to the other substance, So for example, NH3 is there. NH3 has lone pair over it. It can donate the electron. It has 8 electron in its 8 electron incomplete. So NH3 can donate electron to BF3. This is a kind of adduct that is formed in between. So these are some of the modern concepts of acid base. Like you can see, Arrhenius concept give H plus ions, Arrhenius base, OH negative ions it can donate, Bronsted-Lowry acid proton donor, Bronsted-Lowry base proton acceptor. Okay. So these are the conjugate acid base pair. I will explain it to you. Lewis acids are the electron pair acceptor, Lewis base are the electron pair donor. Now what are conjugate acid and base? Okay. So this is an acid, this is the conjugate base of that acid. Means acid has its conjugate base after donating the H plus, and base has its conjugate acid after accepting the H plus. Okay, after donating H plus, it's a conjugate base. After accepting the H plus, it's a conjugate acid. This is the conjugate acid of this base. Okay. Now, with that, if you could understand this, Lewis acid accepts an electron pair, Lewis base donates an electron. I can show you that if H3O positive ion is equal to OH negative ion, what will happen? What is the nature of the solution? If H3O positive is greater than OH negative ion, if H3O positive is less than OH negative ion. Okay. If H3O positive is equal to OH negative, then it's a neutral state. It's a neutral state. If H3O positive is greater than OH negative, then it's an acidic solution. Acidic solution means H plus is greater than. Now, if OH negative is greater than H3O positive, then it's a basic solution. Okay. So, this we have covered. Okay. Next one is if. What is pH? pH is negative logarithm of H positive ions. Negative logarithm of H positive ions. pH is equal to minus log of H positive. Means if H positive ion is going to increase, means the acidic solution is there. Acidic solution, acidity increases, acidic strength increases, then pH is going to decrease. So, okay. So, with that, I am going to explain you that, see, pH of a solution is negative logarithm to the base 10 of the activity of the hydrogen ion. Base 10 is nothing but log base 10 of the H plus ions. H plus ions concentration or activity you can say in the solution. This is the concentration of H plus ions. pH is the negative logarithm of H plus ions. So, how I can define pH in a, suppose if I have HF, HCl, HBr, HF. Okay. So, the pH of the solution, whose pH is high. Okay. See, you need to say that down the group, this is down the group, the tendency to lose H plus ion is high. H plus ions is high. Okay. So, H plus ions is going to F negative is there, Cl negative, Br negative, I negative. Down the group, the size of the atom increases. So, this negative is going to decrease. Means this negative has a space to cover it up. So, there is less electron-electron repulsion and it is more stable. That's why this Hi can easily lose H plus because it is heavy. It is going to have a stable product. Okay. So, this is more acidic. This is the acidic order. Okay. But the pH is opposite to this acidic order. pH of Hi is greater than H, less than HBr, less than HCl, less than H. So, this is the pH order. This is acidic strength order. That depends on the size. Okay. So, we have covered this. Next one is this one. What are indicators? Now I am going to show you. The indicators are the weak organic acid or base which change its color within the limits with changing in pH value of the solution to which it is mixed. So, the indicator is going to change them. These are the weak organic bases and the acids which is going to change the color when the pH of the solution is going to change. Okay. Now, after that, what is common ion effect? What is common ion effect? if there is a common ion effect, then the increase, then the then there is, it is the phenomena of lowering the degree of ionization of a weak electrolyte by adding a solution of a strong electrolyte having common ion to that furnished by the weak electrolyte. See, suppose I have this NH4OH. This is a weak acid, sorry, weak base. Okay, and this is a weak electrolyte, so we are going to get NH4 positive and OH negative. If I am adding strong electrolyte to it like NH4Cl, it will dissociate completely NH4 positive and Cl negative. Okay, now these are the common ions, these are the common ions, and I have explained to you the Lee-Chatelier principle. So by adding this strong electrolyte, what I am increasing? I am increasing the concentration of product. What I am increasing? I am increasing the concentration of product. Then the equilibrium will shift towards the backward direction. Means there is a suppression. Means there is a suppression of dissociation of a weak electrolyte by adding a strong electrolyte to it. Okay, so this is common ion effect. So this is common ion effect. It is the phenomena of lowering of degree of ionization. Means here we have the degree of ionization, means the ionization is going to get decrease on increasing the strong on adding the strong electrolyte having a common ion to that of the weak one. Okay, now next one is calculation of equilibrium constant. How we can calculate equilibrium concentration or equilibrium constant value? Suppose I have AA plus BB giving in equilibrium with CC plus DD. We know that we can write Kc as C power C, D power D, A power A, B power B. Okay. Now for that I need to write initial concentration, then the equilibrium. Initial concentration. Suppose I have initial concentration 1. In the initially, we are not going to get concentration, okay, of the product. In equilibrium concentration, suppose, so in equilibrium, after equilibrium, we are going to get 1 minus x, x. Okay, suppose this concentration is going to get decreased, this concentration is going to get decreased, and this is going to get 4. Ax, you need to multiply with this Ax, you need to multiply with this B, Cx and D. Okay, so I am giving you the value, for example, 400 at 298 Kelvin. So 400 is equal to Cx power C, Dx power D, 1 minus Ax power A, 1 minus Bx power B, because this is equilibrium constant and we need to put the equilibrium concentration here. So I am putting the equilibrium concentration value. By this you can calculate the equilibrium concentration too. If we in equilibrium concentration, because x we are going to get from here if we have the value of C, D and all, and by that we can calculate equilibrium concentration by multiplying. Okay, next one is, what is buffer solution? What is buffer solution? Buffer solution is which resist the change in pH, which resists the change in pH when we add small amount of acid or base in it. Or base in it, which resists the change in pH when we add the small amount of acid or base. Okay, so this is our buffer solution. Next one is, what is solubility product? Solubility product. Solubility product is for the separately soluble solid. Soluble means it do not soluble solid means it do not completely dissolve. For example, AgCl. AgCl solid is in equilibrium with Ag plus aqueous and Cl minus aqueous. Remember, while writing the equilibrium constant, you need not to put the solid concentration. Solid concentration and liquid concentration, you need to take the concentration for solid and liquid always unity. Okay. So here we have solid only. Here we have the Ag plus. Now the solubility product constant Ksp is equal to the concentration of Ag plus because it is in aqueous solution, aqueous state, and Cl minus because it is in aqueous state. Okay. So this is my solubility product constant. This is my solubility product constant. So if I want you to tell how to calculate Ksp for that, Ag plus aqueous plus Cl minus aqueous. Suppose in the initial 1 minus 0, 0, 0, initial concentration. After dissociation means after attaining equilibrium, what you will get 1 minus S means the solubility S and S. Now the Ksp value will be S into S. Okay, the Ksp value will be S into S, so it will be S. So we have covered all the sections, all the points that is related to mind map. I hope I am clear to all of you. Thank you so much.